Hello, welcome to another video of design analysis and the configurable system. Today we are going to talk about high-level synthesis. High-level synthesis is a process where we take high-level languages. For in this instance, we'll be taking C as our high-level language, using which we'll be generating RTL code, and then use that RTL code to run on our FPGA. Here, in order to perform high-level synthesis, we perform three main steps. One is resource allocation, resource scheduling, and binding. In order to do that, for high-level synthesis, we'll have to provide three different inputs. That is the C code, library files, and target frequency. Using this, the HLS tool will perform allocation, scheduling, and binding. We will further verify the design and perform design using simulations, whether it is software simulation or RTL simulation. We will also look about how constraints modify our final design, whether it is timing constraints, resource constraints. And by performing all this, we will end up with a solid RTL code, which we can implement on our FPGA board. Let us look at our C code and see what we are implementing. So this functionality, what we are implementing today is called as a running average of 8 latest numbers. So what it does is it takes continuous inputs from the user, averages and considers only the 8 latest input from the user and generates the average of those 8 numbers. So initially we create a buffer of size 8 and fill it with zeros. Basically we are resetting the buffer every time a user provides an input or the simulation stimuli provides an input, that will be updated to the buffer. Once that data is updated to the buffer, then the average of all the 8 numbers is calculated. So this is the code that performs shifting of the data or inserting of new data, which is provided by the user. So first, we shift the existing values, the top 7 values to accommodate for a new input. The latest input is entered into the buffer. Once that is done, we calculate the sum of all the numbers using a for loop where this calculates the sum of all the 8 numbers. Once that is done, we divide it by 8, basically doing an average of all the 8 numbers and return that back. So this is the main function, not the main function, the main functionality of this program. Coming to the main function, it is basically software test bench. So here you can see we have used preprocessor directive for the if-C. What this means is whatever code is mentioned within this block will be only used by the compiler for software simulation, basically only for C compiler. If it is for RTL simulation, RTL synthesis, this part will be omitted. So what this function does is it reads two files. One is the in data and the out data, and creates a pointer for those, basically a file pointer, and reads all the data from the input file till the end of the file. Once that is done, for each input, it will call the average 8 function, and whatever the output is generated, it is being returned to the output file. So this block of code will be only used for software simulation. Since it is defined in if-C, RTL synthesizer will not look at this code or compile this code for RTL. And here we have defined AV, average 8, as a cyber func process. This means that cyber workbench will treat this as the main function or the top module for the RTL synthesis. In order to proceed with this, as I mentioned before, we need three things for HLS. One is the C code, which I just described. Second is the library file, and the third is the target frequency. So the library and target frequencies are provided at the time of project creation itself. Here we are mentioning it as 50 megahertz, and our library files, since it is an FPGA, the board itself is tagged with the library files, since all the modules are baked into the FPG. We'll include the library files that are connected to the cyclone. Once that is done, basically these details will be provided at the project level itself. Once these three inputs are available with us, we go about compiling the code to see if there is any errors in the C code itself. Once we compile or analyze the code, AVA directory file folder will be created. That means yes, your C code is syntactically correct. We can proceed forward. So here, this is where our RTL synthesis happens. So for this, we have to provide few synthesis options, which can be provided here. Here we are going with all the default options, but our main input will be C2000. That means we are running this at 20 nanoseconds, which is equivalent to 15 petahertz. Rest everything we are keeping at default for this. Once that is done, we will have to look at a few constraints, that is functional unit constraints. Initially, we keep it at auto so that the synthesizer will analyze how many functional units are required. Once the synthesizer analyzes based on our three inputs, RC code, library files, and target frequency, it will analyze how many functional units are required. Uh, this we keep it at auto only at the beginning, and then we change it to manual so that we can have a manual control over the constraints going forward. So since I've already run this, I've changed it to manual. We can look at the constraints, what it has automatically generated. For our adder, it has used four 8-bit adders and three 12-bit adders, which is required to calculate the sum of the eight 8-bit numbers. So this is the data path, what the HLS has created based on our design requirements, where you can see there are 8-bit adders at the beginning, and then these outputs are fed into 12-bit adders. In the quality of results, this report consists of all the details regarding the synthesis. Here in the summary, we can see how many ALFs are being assigned, how many registers, the latency of the whole design, clock period, and critical path delay. From this data graph, we can also view the critical path of our design. We'll have to go to view, critical path, and we'll highlight what is the critical path of our design. Here it is input 0 through 8-bit adder to first 12-bit adders, basically through all the 12-bit adders and finally to the output. Now with this selected, we'll switch to C code and it will immediately point us the C code in which is involved in the critical path. We can also see how functional units vary the whole design and the results as well. We'll go to functional constraints, modify our constraints. Let's say we just we'll just ask the design to use only two 8-bit adders and just two 12-bit adders. We'll apply, and based on that, we'll have to resynthesize the design. Once the resynthesis has been done, we'll again be prompted with the quality of reports where we can see earlier it was 63, now it has jumped up to 93 ALFs, and critical path delay has doubled right now. We'll go to data path viewer, data path, and you can see there is a FSM created for this. Since we are asking the design to run with less number of functional units than it is automatically generated, basically to run a maximum parallel operation, it will create a finite state machine where it performs resource sharing, where the same adders, after it performs addition at one point, is being connected to other inputs to perform addition in the next cycle. So due to these changes, we can also see latency has increased to 2 cycles. Since the same resources cannot be shared in the same cycle, in one cycle, certain resources are assigned to certain inputs. Once that evaluation is done in the next cycle, the data path is modified to accommodate for the other inputs. So using cyber workbench, we can also perform logical synthesis where using the generated RTL, we can generate the bit stream that is required to configure our FPGAs. For logic synthesis, we have configured the Cyber Workbench to use Quartus Prime as the synthesis tool. So using the logic synthesis tool, which is tagged to the Quartus Prime application, we will be able to generate the bit stream, which will be further used to configure the FPGA board. If you look at the files for the logic synthesis, it has taken the RTL that is as Verilog code. In the projects, we can see that's generated QPF file, which is basically Quartus project file, and also it has generated better reports. Here we can see the Quartus reports on how our design is being fitted on the board and also the resources being used. Now that we have gone through how HLS is performed, we'll also look at design verification. First step of design verification, since here we are starting with the C code, we'll go about software simulation. Basically, what it does is at software level evaluates the design. So for the simulation work, we have multiple options: behavioral, cycle accurate, RTL, on board. So for behavioral, we have three options. We can either code it in C, bit accurate, or system C. We'll do this software simulation in C. I've already done that since with my high-level language design, I'd also given it software simulation code here on the test bench and defined it inside the if test blocks. Here you can see the input data and the output data. So these are the input streams that I gave it, and these are the generated outputs. We can also perform RTL verification where we verify our Verilog code with timing constraints. I've used the same input file, input stream to verify the output. Here, but main changes is here we'll have to append or prepend few zeros to match the cycle. Since in this design our latency is just 1, we don't have to worry about duplicating the values or waiting for the output to be generated in a multi-cycle operation. But we'll have to consider one more process in RTL verification, that is it has follows something called as verification of golden output to generated output. Golden output is basically the output generated by the software simulator or during software simulation. So in one cycle where we provide an input, it will generate the output and verify if that output is same as the golden output. This leads to a lag in the system where it will take an extra cycle to generate the output. So here we can see an offset of one cycle in our. So to accommodate for that offset in our input, our final value will be 0. And initially in the software simulation, we just had two zeros, but here we'll be having three zeros, where the first zero is just an offset zero. To accommodate for the simulator to perform evaluation between golden data and the generated data. Once we run the RTL simulation, a transcript file will be created. Here, the main thing that we are going to look at is uh, matching between golden output and the generated output. Here, you can see for each input and output, it will show you what is the output, what was the expected output, and whether it matched or not. For our stimuli, we gave in 24 numbers, 24 inputs, and for all of them, the output. With during designing with all these variables that we can tweak, we can have multiple different designs, whether we are changing the frequency, whether we are changing the library files, or let's say we change the functional units that are being used. Now, how do we decide which design is the best? So Cyber Workbench provides us a graphical view of these outputs where we can graphically evaluate each design's metrics. So for that, we'll go to synthesizer window. where it'll have a cumulative of all the design synthesis that we performed during the cycle. Here I have maintained three designs for evaluation. First design is where the auto-generated design, where the only modifications I've done is here with the functional unit. The first design point consists of four 8-bit adders and three 12-bit adders. For the second design point, I reduced the functional units where I had two 8-bit adders and two 12-bit adders, with which you can see the number of ALETs increased and also the latency. And for the final design, I selected only one 12-bit adder and zero 8-bit adder. This increased the latency to 7 and also number of ALETs reduced since not many functional units were there. So by this, we can graphically see the performance of each design, and this helps us to perform a Pareto analysis and select our best design out of the bunch. So yeah, that is the high-level synthesis of using C code and using high-level synthesizers like Cyber Workbench to generate the RTL, perform design verification, logical synthesis, design space exploration, and evaluate how multiple factors related to the synthesis affect the overall design and how to select the best performance design out of the bunch. We also perform simulation to see if our design works and get more insight about our design. Thank you. Have a great day.